So you've probably built a few predictive models, right? You draw that straight line through your data and it kind of works. But let's be real, the world is rarely a straight line. Today, we're going to get into the good stuff, how to build models that can handle the curves and the complex relationships that you see in real-world data. This is where models go from just okay to actually being powerful. All right, here's our game plan. First, we're going to talk about why straight lines just don't always cut it. Then we'll get into the fun part, modeling curves and interactions. After that, I'll show you a super powerful technique called data transformation. And finally, we'll look at how to get the computer to help us pick the best variables for our model. Sound good? Let's do it. Okay, first things first, we have to understand the problem before we can fix it. So let's talk about why we need to move beyond just thinking in straight lines. This is all about recognizing when our simplest tool isn't the right one for the job. I mean, it's the first thing we'd all learn, right? Draw a line of best fit. It's simple, it's clean, it's so easy to explain. But what happens when you actually plot your data? You take a step back and you realize, yeah, that's definitely not a line. And here is a perfect example of what I'm talking about. Look at this. The data points have this beautiful U shape to them, but our simple little regression line, it's just plowing straight through the middle, completely missing the entire story. This is a huge flashing sign that says, hey, we need something better. So how do we do that? How do we give our model the power to see what we see, to capture that complexity? Well, let's dive into two of my favorite techniques for doing exactly that. The first tool in our new toolkit is the second-order model. Now, that equation might look a little intimidating, but the key is that little x1 squared term. All we're doing is adding a squared version of our variable, and that one simple addition gives our straight line the ability to bend, to follow a curve. It's what lets us perfectly trace things like that U shape we just saw. Okay, but what if it's not just a simple curve? Things get really interesting when you have two variables that, well, they work together. Their combined effect is something totally different than what you'd expect by just looking at them one by one. Let's make this super clear with an example from a shampoo company. They're trying to figure out how pricing and advertising affect their sales. So they ran a few tests, and here's what they found. Now pay close attention to this. When the shampoo is priced at $2 and they double their ad spend, boom, sales jump by 347,000 units. That's a huge return on their investment. But, and this is a big but, watch what happens when they raise the price to $3. That same increase in ad spending, now it only gets them an extra 43,000 units. The power of their advertising just fell off a cliff. And this is the whole point. You can't just ask, how effective is our advertising? The answer is, well, it depends. It depends on the price. The two things are tangled up together. You can't understand one without the other. This is called an interaction. So how do we model this? Simple. We create what's called an interaction term. We literally just multiply the price variable and the advertising variable together. That new term in our model mathematically captures this synergy, letting the model understand that these two things work together. It's brilliant. All right, next up is another incredibly powerful idea. You know, sometimes the model isn't the problem, it's the data. Or rather, it's the way we're looking at the data. If we can just change our perspective a little bit, the true pattern can suddenly become crystal clear. Check this out. On the left, we're looking at the errors from a model trying to predict a car's miles per gallon. See how the errors get bigger and bigger as the prediction gets bigger? That fanning out, wedge shape, is a major red flag in regression. But look at the right. All we did was take the natural log of the MPG, and, like magic, the problem is gone. We're left with this nice, clean, even band of errors, which tells us we've got a much, much better model. Now, when you transform your variables, it does change how you interpret the results. But don't worry, this table is basically your decoder ring. So in that car example we just saw, which was a log-level model, our coefficient now tells us the percentage change in the outcome for a 1-unit change in the predictor. And honestly, sometimes that's a way more intuitive way to think about it anyway. Okay, so now we've got all these potential new variables, right? We have squared terms, we have interaction terms, we have transform terms. Our list of possible predictors is getting huge. How in the world do we choose the best combination to put on our final team? Well, here's one popular way to automate it. It's called forward selection. Think of it like you're building a basketball team from scratch. You start with an empty court. Then you add the one player, your single best variable, that helps you win the most. Then, with that player on the court, you add the next player that helps the team the most. You just keep adding the next best player until adding anyone else doesn't really improve the team's score. Backward elimination, as you might guess, is the total opposite. Here, you start with everyone on the court at once. Every possible variable is in the model. Then you look for your weakest link. Statistically, that's the one with the highest p-value. If they're not contributing much, you cut them from the team. Then you reevaluate and cut the new weakest link. You just keep trimming the fat until everyone left on the team is a statistically significant player. So just to nail this down, forward selection is a builder. It starts with nothing and adds pieces one by one. Backward elimination is a sculptor. It starts with a big block of marble and chips away the pieces that don't belong. They're both super useful ways to help you find a really strong model without getting lost in the weeds. All right, let's bring it all home. Building a fantastic model isn't just about crunching numbers. It's really an art form, a blend of using the right statistical tools and then thoughtfully interpreting what they tell you about the story in your data. So let's quickly recap our new and improved toolkit. We now know how to use squares terms to let our models bend and follow curves. We can use interaction terms to capture when two variables team up. We can use log transformations to fix wonky data and get a clearer view. And we have automated methods like forward and backward selection to help us choose the best predictors from a crowd. It's this mix of art and science that leads to truly great insights. And really, that's what this is all about. At the end of the day, a model is just a story. All these techniques, curves, interactions, transformations, they're just ways to help you listen more carefully. They help you uncover the real, nuanced, and often surprising story that is hidden inside your data, just waiting for you to find it.